Hey everyone, and welcome. Today we're going to put on our detective hats because we are diving deep into a really fascinating linear algebra problem. Think of it like a case with two parts. It's got twists, turns, and, of course, a few mathematical suspects we need to investigate.
And here it is, the central mystery we need to solve. Can you actually take a matrix that is not symmetric, apply a very specific kind of transformation to it, and have it pop out on the other side looking perfectly symmetric? Is this some kind of mathematical magic trick, or is it just flat out impossible?
So, here's our game plan for cracking this case. First, we'll tackle that symmetry challenge, and we're going to do it by hunting for a logical contradiction. Then, we'll open up a whole second case file on something called row equivalence, where we'll investigate a couple of claims about kernels and images. And finally, we'll wrap it all up and look at the core takeaways. Let's get into it.
All right, so first up in our investigation, let's meet the key players. We are dealing with two square matrices, and we'll just call them A and B. They're the same size, right? But they have one absolutely crucial difference that is really at the heart of this entire mystery.
So on one side, you've got matrix A. We're told, explicitly, it's not symmetric. That just means if you take its transpose, flip it across its main diagonal, you get a totally different matrix. Then, on the other side, we've got matrix B, and this one is symmetric. Its transpose is exactly the same as the original.
Okay, so here's our mission. We have to prove that it is impossible, literally impossible, to find a special kind of invertible matrix, we'll call it P, that can satisfy two conditions at the same time. The first is this transformation. B equals P inverse AP, which is called a similarity transformation. But here's the real kicker. P also has to be an orthogonal matrix, which is a fancy way of saying its transpose is also its inverse. Our job is to prove this whole setup just can't happen.
So how in the world do you prove something is impossible? Well, one of the most powerful tools in any mathematician's toolkit is what's called a proof by contradiction. The idea is simple. We're going to assume that this magical matrix P does exist, and then we'll just follow the logical clues until the whole argument completely falls apart on its own.
Let's walk through the evidence step by step. We start by assuming our matrix P exists, which gives us our starting equation. Okay, now, here's the key move. We take the transpose of both sides. Now, we have to remember two crucial facts from the case file. B is symmetric, which means B equals B transpose, and we know P is invertible. So when we use those facts to set our two expressions for B equal to each other, we can just cancel out the P matrices on both sides, and what does that leave us with? A pretty stunning conclusion. A equals A transpose.
And boom, there it is. That's the contradiction. Our assumption logically forced us to conclude that matrix A is symmetric. But wait a minute, the case file, the very first thing we were told was that A is not symmetric. You just can't have both. It's a logical impossibility. So that means our initial assumption had to be false. It is, in fact, impossible to find a matrix P like that. Case closed on part 1.
Okay, with our first case solved, let's turn our attention to a slightly different kind of mathematical puzzle. This next investigation is all about the consequences of a really common procedure, row operations. We've got two linear transformations, T and S, whose matrices are row equivalent, and there are two claims about them that we need to either prove or debunk.
But before we go any further, let's do a quick refresher. What does row equivalent even mean? Well, it's pretty simple. It just means you can turn one matrix into the other by using those basic row operations we all know. You can swap two rows, multiply a row by some non-zero number, or add a multiple of one row to another. That's it.
So, here are the two claims on the table. Claim 1, if two matrices are row equivalent, does that automatically mean their kernels are identical? And remember, the kernel is just the set of all the input vectors that a transformation squashes down to 0. And then, claim 2, does it also mean their images, the set of all possible output vectors, are also identical? Let's find out.
We're going to start with claim number 1, the one about the kernels. Now, our intel suggests this claim is true, so we're here to see if we can confirm it.
And yep, this claim is absolutely true. Here's why. The kernel is really just a fancy name for the set of all solutions to the equation matrix times vector equals 0. And one of the most fundamental rules of linear algebra is that doing row operations, swapping, scaling, adding, doesn't change the final solution set for this specific type of equation. So, since the matrices are row equivalent, their solution sets have to be identical, and therefore their kernels are identical. Simple as that.
All right, now for the second claim, the one about the images. So just because the kernels match, does that mean the images have to match too? For this one, we're not trying to build a big proof. We're just looking for one single piece of evidence that proves it wrong. What I like to call a smoking gun counterexample.
It kind of feels intuitive that they might, right? I mean, the operations are just rearranging things inside the matrix. But as we know, intuition can sometimes be a little bit misleading when it comes to linear algebra, so let's actually test it.
So, here is our counterexample. Meet the matrices for T and S. As you can see, a single row swap is all it takes to turn one into the other, so they are definitely row equivalent. And we can confirm they do have the exact same kernel. But what about their images?
Okay, now let's look at their images, which are just the spans of their column vectors. The image of T is the span of the vector 1, 0. In other words, it's the x-axis. But the image of S is the span of the vector 0, 1. That's the y-axis. And this just brilliantly shows the point: the x-axis and the y-axis are most definitely not the same space.
And there you have it. We found our smoking gun. We have two row-equivalent matrices that produce completely different images. So the claim is officially 100% false. Case closed.
So after cracking two cases back to back, what did we actually learn here? What's the point of all this? Let's distill this whole investigation down to its core lessons.
So what are the big takeaways from all this? First, we saw just how powerful a proof by contradiction can be for showing that some mathematical ideas are just plain impossible. Second, and this is really the core insight from our second case, we learned that row operations kind of have a split personality. They preserve the kernel, which is the solution space of a matrix. But, and this is a big but, they do not necessarily preserve the image or the column space. That is such a subtle but critical distinction. And finally, we learned that sometimes the absolute best way to test a bold claim is just to find one simple, elegant counterexample that proves it wrong.
And all this leaves us with a final, thought-provoking question to chew on. We've just seen that row operations affect the kernel and the image very differently. So what other mathematical concepts or operations out there seem almost identical when you first look at them, but are actually hiding fundamentally different consequences right under the surface? It's a great reminder to always dig a little deeper. Thanks for joining me.